In this video you can see how I try to optimize the coupling between the two stages of this selective amplifier, which is also intended to be an oscillator. The crystal here injects a current into the JFET. The output impedance of the crystal is about 50 ohms, and the input impedance of these 6 parallel transistors is in the order of 20 ohms. The current then creates a voltage across this transformer. The impedance here is determined by the impedance here through this transformation. And it is not ideal. There are reactive components, and I think they degrade to some extent. There is also one thing, and that is losses here lower the impedance off resonance, which means that this amplifier gets more gain far from the oscillation frequency. So I want small losses and a transformation that is resistive to resistive over a large impedance range. As a first step, I want to investigate the Q of the coil, the primary coil, and I use this simple setup, network analyzer input and output, and I look at the notch that will happen when there is a parallel resonance here. First I have a look at the 6 material, the yellow core. Here is what I see, minus 57.06 decibels. Next I try material 2, the red core. I have not changed the tuning capacitor, and I have saved the trace from the yellow core. Now I see minus 57.32 instead. And I changed the scales so we can see the difference better, but it is very small, 0.3 decibels or something like that, but it is in the right direction. I have connected the old transformer like this with a secondary connected to the output and the other end hanging free in the air. That is to take the capacitance between the windings into account when I set this capacitor so I can use it to find the correct inductance of the new transformer. 45 turns on the primary and 8 turns on the secondary, and 0.1 mm Teflon tape in between to reduce the capacitance between the windings. The frequency is close enough now, and the Q is a little higher. I will now compare the two different transformers. This way, I change this resistor from infinity, means no resistor, until I find the value that changes the phase of the signal that goes through here by 10 degrees. This is without any resistor, means infinite resistance. The intense line is the phase, and now it is the level, the amplitude, minus 65 or minus 64.8, and the phase angle very close to 0. I will now put a resistor in place. Now the phase is minus 9.3 degrees, and the loss, I have to change the scale, a reference level, let's say minus 20, and you can see I have minus 28. Now the important thing is what resistance value I needed to get this. The resistor was 106 ohms. Now I am doing the same test with the new transformer, Without any resistor I see minus 58.1 dB. Here the phase angle is 9.9 degrees, 10 degrees as before, but the loss is minus 25.7, and that is with 52.7 ohms. I have added copper foil on top of the windings. That's to prevent the magnetic field from going outside the iron. As a consequence, I have had to increase the capacitance a bit, because inductance is the integral of the magnetic field lines, and they have to occupy less space now because they can't penetrate the copper. The loss with no resistor now is minus 58.3 dB. Now, with a 10 degree phase shift, well, 9.7, the loss is 25.3, and that is with 45.8 ohms. I have covered the windings with copper to squeeze the magnetic fields into the core, and I need some more capacitance to tune it now for a phase angle of 0, the weak trace here, and then the attenuation I see is 58.5. Here the phase angle is almost 10 degrees, like before, just a little bit below, and the attenuation is 24.7. I think I want to load the drains by 1.5 kilo ohms. So I have put 1.5 kilo ohms between input and output from the network analyzer. And then the attenuation I see is 23.7 dB. So I connect like this, find the resistor that gives me 23.7 dB attenuation through here. And then what I want is that adding or removing that resistor should not change the phase angle much. Here is close to 23.7, and the phase angle is minus 8.1 degrees. This is the new transformer. The resistor I need for that is 42.5 ohms. Now I'm looking at the old transformer, and I have tuned the resistor for 27.3 decibels. And then the phase angle I see is minus 5.7 degrees. The resistor I need for that is 90.5 ohms. The result of this experiment is not of much value, I think. The only thing is that the loss from here to here with the resistor giving 10 degrees phase shift is much larger here, and then it becomes smaller, and with screening of the magnetic field around the core it becomes even lower, and with more screening even lower still. And this means that energy going through here is dissipated somewhere, so the notch is not as deep anymore here. And that means that energy is transferred to the resistor, which is what I want. But this is not very clear, and I don't think this experiment is of any value. This experiment is more interesting. The phase shift is not so important. I have selected a resistor to give a 23.7 loss from here to here, equivalent to 1.5 kilo ohm from here to here. So the resistor I found, 42.5 ohm for the new transformer, transforming to 1.5 kilo ohm. That's a factor of 35, gives a turns ratio of 5.94. And the actual turns ratio is 45/8, 5.625. And the ratio between the theoretical and the observed transformation is nearly 1, 0.947. The old transformer, it required 90.5 ohms, and doing the same operations I find the theoretical turns ratio would be 4.07, but the actual is 4.7. 47 turns and 10 turns. And the ratio between theoretical and actual turns ratios is 0.866. This is far from 1 as compared to this one, which means that the new transformer should be much better. I will now use this configuration. I can leave this switch open, which means I have only the transformer and I look for the impedance. And of course then I want it as high as possible, because a high impedance here means there will be lower noise from the next amplifier, which is a grounded gate amplifier. Then when I switch in 5.6 kilo ohms, that should simulate the output impedance from the previous stage when the frequency is at the center of the crystal. Because with 50 ohms on the source, the impedance on the drain will go down, and I think to something like this. And then I want the impedance here as low as possible. The ratio of the impedance with a switch here or here should be as high as possible to make the gain of the next amplifier as high as possible on the center frequency and as low as possible far from the center frequency. And then I can also add a 1 pF capacitor to see how much that changes the impedance. And of course this is tuned for the impedance here to be resistive when the switch is in the upper position. I look at the new transformer first. The switch is that I can solder the resistor or the capacitor to the BNC connector, and there is nothing connected to it, it's just a support mechanically. And these two is the tuning capacitor, a big one for coarse tuning and a small one for fine tuning. With the switch open means nothing connected. I see 2.14 kilo ohms and a small reactive components, 49 ohms. With the resistor connected, I see 150 ohms resistive and -6 ohms reactive. With the 1.0 pF capacitor connected, I see this 88 ohms resistive and -400 ohms reactive. So a very small mistuning makes a very big difference. The old transformer gives 2.0 kilo ohms when the switch is open, and the tuning capacitor is set for minimum reactive impedance. With the resistor connected, I see 200 ohms and -1 ohm reactive. The impedance ratio caused by the 5.6 kilo ohm resistor being connected or not is 14.3 for the new transformer, and it was 10 for the old one. The improvement is a factor of 1.43. So the voltage gain on the resonance should be 1.4 times larger as compared to the gain on the white noise floor off resonance with the new transformer, and that is 3 decibels. The resonance of the new transformer is narrower. 1 PF mistuning will cause an impedance ratio of 5, while 1 PF mistuning will cause only 3.5 for the old transformer. It means that the very low noise off resonance will start to rise when the separation from the crystal frequency becomes larger, and that will be more sensitive now than it was before. This could be compensated by some analog filter, probably. I have disconnected the first filter and just measure with one crystal and without the compensation for the crystal capacitance. Here is the input impedance, 48.58 on the resonance and 49.91 or 92 at the off resonance. So the equivalent on the resonance, I see 48.58 from here to here. Off resonance, the crystal isn't here, and I see 49.92. And that gives me this equation. This gives me the impedance for the crystal. X is 1810 ohms. The power ratio between the two resistors is 36.2 times, and that is 15.6 decibels. And I want to send about 300 microwatts into the crystal filter to dissipate in the crystal and in the load resistance, that is the source of the FETs. So I want to send plus 10 dBm into the unit. Here is the frequency response, and Q is 1.088 million. I have placed a 15 ohm resistor from here to ground. That means from the sources to ground. The bright track is the result I get now, and I have saved the old one, which is the weaker track. The gain is reduced by about 6 decibels, and I can go for data divided memory and recent, and it says 6 decibels and here a little bit less. But this means anyway that the input impedance is close to 15 ohms. The power I send to the crystal goes into the crystal itself and the impedance of the amplifier. So the power in the crystal is 50 divided by 50 plus 15, which means it is minus 1.1 decibel that goes into the crystal, referred to what goes in here. I want to send 10 dBm into the unit, minus 15.6 dB. That was the power ratio between the crystal and the 50 ohm load on the input. And then minus 1.1. That is a total minus 6.7 dBm. Means 212 microwatt to the crystal itself. And that seems very reasonable to start with. I'm sending plus 10 dBm into the unit, and note, set the markers for the level I find on the output. I have reconnected the components on the input side, means this transformer in particular, and the resistors together they give 50 ohms, and there is some loss in the filter here, so I had to add a 5 ohm resistor in series to see 50 ohms from here. I have also disconnected these resistors, so there is no current through the transistors. I then set the trimmer here to get the same signal level as I had with this arrangement. The adjustment here was very small, 0.3 decibels only. The response looks very similar, and Q is now 1.08 million. I save this, and then I connect 1.1 kilo ohm from here to ground to reduce the impedance on the drains. The signal level is then lower by slightly more than 6 decibels, and Q has gone up but very little, so there is no improvement on the Q, even though the impedance on the sources should have become a little bit lower now. I'm sending 10 dBm into the oscilloscope through a low-pass filter, and then I put the markers on the signal level I observe. Here is the amplitude response again, and then I look at the phase, and it passes a 0 at the same frequency as the signal is strongest. So now I can make an oscillator out of this. This does not look promising at all. The average noise is 124.8. That's the average from 0.22 Hz up to 3.7 Hz. And in particular, here I should expect a yellow trace about 3 decibels below the other two, but it is the same, which means that the noise from the oscillator I'm testing is higher than the noise from the local oscillators I have. I have reduced the power by about 7 decibels by replacing the 4148 diodes by Schottky diodes BAT42 as the limiter of the feedback loop. And I will wait until tomorrow. It's late now. The average is now 129.13, and I will expand the graph and then take the data and plot on paper. At 10 Hz, I'm into the noise floor at 153.3 or something like that. I have plotted on the curve where I have the Wenzel measurement. The F-3 line here fits to the point down here, maybe, but then the slope is bigger, but at 0.15 Hz it is below what I had with the Wenzel oscillator. So there are several phenomena involved, and I don't know what is going on. I have gone back to this circuit here and also restored full power by going back to 4148 diodes here. Already after 3 minutes I can see that I have a big problem with that input circuit. I now see minus 131 for the average. I have disconnected here and retuned that capacitor. This gives me 129.5 or something around that, but I had minus 131 without that transformer. But now the noise is very high, and I have not changed anything else. I just gone back to what I had before, which was then good. And it's very obvious when I look here in the baseband graph. The noise spectrum is much wider. Here I have hit the box with a small hammer a couple of times, and it has a dramatic effect. You can see the width here is larger than here, and it's more visible in the baseband waterfall, as you can see here, compared to that. And the effect on the average noise is very significant. This is quite good for a filter with just one crystal. This means I have a mechanical problem somewhere. After all, it was not difficult to find the mechanical problem. I had connected and disconnected the connectors here and here great many times without cleaning the connectors, as one should do every 5 or 10 times they are connected and disconnected. So I have cleaned the connectors and I haven't seen the problem since then. I have found that this input is much better than this when I eliminate all the noisy components that could be here. And even so, this does not work well. And now I think the reason is that this is a resonant circuit that will short-circuit high-frequency components that come from here. So what I do by connecting this resonator is to change the performance of the amplitude limiter. That's a theory, and I will try to see whether it fits to the real situation. Here is the result without the resonator on the input. I will take out the numbers from this and plot to see the shape of the curve before I try to put back the resonator with a serious resonating link on the feedback output. At very close offsets from the carrier, this measurement is not correct. The correlation here can never be higher than the weakest of the oscillators. So there must have been an event with strong noise very close to the carrier. And long ago, because I don't see it on the waterfall. There is also a problem at larger offsets. At 5 Hz I can guess 147.5, but then there is an interference problem. 10 Hz looks like minus 157 here, but it's pretty uncertain. The imaginary part scatters from here to here, and you can see the interference is here. I don't know what it is. Maybe I was knocking on the table. And you can see in the waterfall, now when I'm sitting here and talking and vibrating things, I get interferences. Here is the F-3 line now, from the points at 3 Hz up to 5 Hz. And then it bends, it becomes much steeper. And here I know it is a measurement error. But what about the region in between? I don't really know. So I will wait quite some time to see what will be the result of the new measurement of the same thing. I have decoupled the cables mechanically by moving them into the foam plastic here. And the same for the output coaxial cable and the ground cable. And then I restart the measurement. Now it is doing the average from 1 Hz to 15 Hz. And it was now 150.14. And I restart here. The noise from 1 Hz to 15 Hz is just a single dB lower, but the curve looks perfectly fine now. At 10 Hz it's too noisy to give an accurate reading, but I would say something like that, 156.5 perhaps. And the usual from 0.22 to 3.7 Hz, I see 130.75 without any interferences on the curve. Very close to the carrier, the difference is very large. For example, at 0.15 Hz here, it is 1, 2, 3, 4 decibels below the best of the uncorrelated curves, which means that this oscillator is actually a little better than the oscillator I have in channel 2, and much better than the one I have in channel 1. Here are the differences between the two measurements with interference and now the latest one. It is 9.4 decibels at 0.15 Hz, and it is 0 from 0.7 up to 3 Hz. And then at 10 Hz it is 0.5 dB, but that measurement was just an estimate. The results now are the red points in this range, and then it follows the yellow ones down here. And this one has moved up half a dB, so it comes exactly on the f-3 line from these points. I have changed this amplifier stage, so it's much simpler now with a much lower component count, but it should work exactly the same way. And this is a bifilar, 35 turns, and the tuning capacitor is now here rather than here. So I have a DC return this way and can tune with a smaller capacitor. This is tuned for minimum voltage at this point, because I want the impedance here to load on the drains of the JFETs in order to make a low impedance for the crystal to see. Now I'm feeding about 12 dBm into here from the Wenzel oscillator with currently a 1 dB attenuator. And now I'm going to look at the limiter stage here. And I have not the proper output circuitry yet, because here I need a buffer amplifier later on, with 180 ohms as the load on, well, in series with 50 ohms in parallel with 75. That's about 200 ohms, which is a suitable load on the drains of these transistors. I have a 50 ohm dummy load connected here all the time during these experiments with the limiter. First I look at the signal without any limiter, and then I get minus 118.5 at 0.2 Hz, and at 0.8 Hz I see minus 135 dBc per Hertz. So this is the Wenzel oscillator through my selective amplifier. Then the limiter I have been using quite often with 1N4148. Then I see minus 95 and minus 119, and that is a loss of 23.5 decibels at 0.2 Hz. That's a lot. And at 0.8 Hz I lose 16 dB. And this is amplitude noise, but there will be some AM to FM conversion in the unit probably. So this is maybe an explanation why I have seen strong sideband noise at very close spacings at 0.2 Hz. Then I add this resonant circuit that I'm using primarily to set the phase angle right, but it improves. It is 2 decibels better at 0.2 Hz and 3 decibels better at 0.8 Hz. But still it is a degradation on the signal by 20 decibels or 13 decibels. Next I try this, which has been successful in some earlier experiment. There is still a significant loss on the signal. This circuit is adding amplitude noise by 19.5 dB at 0.2 Hz. So I continue and I add a second series resonance and still use 1N4148. And now the loss is 20 decibels at 0.2 Hz and 9 decibels at 0.8 Hz. Still discouraging. Next, I use Schottky diodes instead. They are a little bit better. So the loss is now 14 decibels, quote, only, unquote, and at 0.8 Hz, 3.5 dB. Then I try some other Schottky diodes, and they are much better. The loss is only 1.5 dB at 0.2 Hz and 3 decibels at 0.8 Hz. Next, I feed twice the voltage into the same circuitry. And the result is degraded significantly at 0.2 Hz, but it is improved at 0.8 Hz. So actually I have an improvement at 0.8 Hz, 1 decibel only, but I have a loss of 11 decibels. And before, with the lower feed voltage, I had 1.5 decibel loss here. And next, I increase the impedance by putting 120 ohms here. That makes something that I cannot read anymore. The noise is below 135 and minus 144. And the improvement is 17 decibels at least, and at least 9 decibels at 0.8 Hz. So minus 134 at 0.2 Hz, that's here. And I have negative values on the real part, and the imaginary part is the red dots here. So probably the noise is below the here. And at 0.8 Hz, well, at this time I see negative values at this particular frequency, and I guess that at least below minus 144. That's this line. So this is very good, better than I can measure with the equipment that I have. My selective amplifier now runs as an oscillator. Here I'm looking at the amplitude noise very close to the carrier. 0.1 Hz minus 118. 0.2 Hz minus 130 or so. This is a very sensitive indication on glitches of amplitude noise. I made a measurement previously, and then I started to evaluate it here, and something happened, and that was in the measurement system. I was using these attenuators and they are a little bit sensitive for vibrations because they are long and heavy. So something happened when I touched the table. That made this amplitude noise go from about 120 to 96. That's 24 decibels. So I'm looking at this screen before starting the evaluation, and I will check it afterwards. I have 77 averages now. While taking down the numbers from this column, I seem to have made a mistake making too much vibrations here. So I will check the amplitude noise at close range. And it has changed. It was 118 before. That's down here. And now it is 98. That is a 20 decibels loss. The other measurements are much less influenced by this little accident, but I will try to make these events less likely. I think they are related to connectors on the two-channel receive system. I have gone through the usual procedure of cleaning connectors. And here is what the cotton tops looks like. This is the unused one. I have had this into 4 different BNC female connectors. This is from the center pin of a male connector. I'm using isopropylic alcohol for the cleaning. Now the close range noise looks okay again. 0.1 Hertz minus 117. But I will have to wait for a while to get it down a little bit more. It is just 14 averages now. The average phase noise from 0.22 to 3.7 Hertz is minus 170. Is minus 131 or minus 130. Only 18 or 19 averages. I will have to wait quite some time to get a stable value here. Now it happened again. I got this pulse here. Amplitude noise. So it has gone up from, was it minus 118 to minus 82. So I have to reset and leave the place while it is collecting data. I don't know what the instability might be. I have vibration isolation in 2 steps, foam plastic, a heavy piece of steel, more foam plastic, more heavy steel, and then the oscillator box. So it is pretty well isolated, but the two-channel receiver there is not well isolated from vibrations. These are the phase noise values I have observed now. Here, 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 and there is the straight line. And then it falls off and becomes much better. Now, this is most likely an artifact because the output impedance is not 50 ohms. So I don't have the room temperature noise from the output impedance. It is a very high impedance right now. But I can see here it is about 2 decibels better than the Wenzel oscillator. And I think that's pretty good for an oscillator with just a single crystal in it. The frequency scale is up here, 0.5 Hertz, 1 Hertz. And that's where it starts to become incorrect. So I am measuring from 0.1 Hertz up here to 0.4 Hertz or so, reasonably accurately, I think. I have increased the power by 2 decibels, and I want to see whether that makes a difference. But during the measurement, a little more than 6 hours, I have had 2 occasions here and here when there are amplitude glitches. And of course I can see that here on the close range amplitude noise. The average is far above the red and blue dots, which are the uncorrelated spectra. So there was a spike in the amplitude noise here, and that has to be during these events. And this affects the phase noise also, but not very much. And I can see when I compare the numbers, the average from 0.22 to 3.7 Hertz is now 113.10, but before it was 130.62. That's half a dB on the average. And if I look at the average very close, from 0.02 Hertz to 0.37 Hertz, it has degraded from 91 to 86. So this is something that is fairly slow, but rather strong. And of course, in the amplitude noise, well, I didn't even note it because it's so high. It is what you can see here. I have reset the collection of average sideband noise, and there have been no glitches since then. It is 3 hours and 41 minutes now. And now I can see the close range phase noise at 0.1 Hertz. It's 91 decibels now. The close range amplitude noise is below what I can measure. The imaginary part, the red dots here, are at the same level as the real part, and in this range the real part is negative. But the level down here is minus 132. So there have been no amplitude glitches. When I look at the amplitude noise on a compressed x-axis, I see few blue points. Most of the curve is white, which means that I can see a sideband noise signal, but it is of the same magnitude as the imaginary part, so it is below the level that I'm seeing here. And I can guess that starting at 0.1 Hertz, it is below minus 130 dBc or so. So the higher power level has not destroyed anything. It seems to be just a little better than I had before. I have moved the cable that came out from this oscillator down here and connected it to the one with the RAID tape on it. That comes from here, and I've set the generator to 12.4 dBm, and that gives exactly the same signal level that I had when running the oscillator. I then connect the same cable to the oscilloscope, which is set to 50 ohm input impedance. And then I can read the peak-to-peak level 2.32 volts. This is the most accurate power measurement that I can do. 2.32 volts peak-to-peak and squared, and divide by 400. Divide 400. It gives me 13.45 milliwatts. And 13.5, that is 11.3 dBm. I have increased the signal level by another 2 decibels. And here is the average from 0.22 to 3.7 hertz. Starts at 129, and when I look over time it goes down to 127, 128, 127, 128, and it stays the same. Now, when looking here, there is a dramatic difference starting at this time. So when I go for the amplitude noise, I see something different. There is now very strong amplitude noise at -84 at 0.1 hertz, and the average correlation and the uncorrelated spectra are at the same level. You can see the blue and the red dots, half the 1 dB above the average correlation. So there is amplitude modulation now, and I don't know how that happens. Maybe it is something that can be fixed. I've subjected the box to aging in the oven at 64 degrees for 2 hours. The phase noise I have seen at 11.3 dBm output comes here, the rectangular boxes, and here, and then exactly on the same level as before, but down here they are a little bit higher, and 1 dB here and here, and that is probably because the error of having an incorrect output impedance becomes smaller at a higher power level. So it seems that the bending upwards here was caused by whatever is causing those glitches. And I have a hope now, after heat treatment for a while, maybe the source of those glitches has become less dominant. And I have a small hope, maybe the heat treatment makes these amplitude noise events less frequent, or maybe not present at all anymore. After the heat treatment, I have not seen any glitches from the very low frequencies in the amplitude, but the general performance at close spacings has degraded. I can see in the table here the average from 0.02 to 0.37. It's this line. It dropped from 92.7 to 89.3. And similarly, from 0.05 to 0.75, dropped from 105 to 103. That's 2 decibels on the average noise. And here it was 3.5. But at larger offsets, for example from 0.5 hertz to 7.5 hertz, it's gone from 140.86 to 140.47. That's just a small difference. And at wider separations there is too much noise, so this doesn't really mean anything. And if I look at the values I read, at 0.1 hertz it's degraded from 91 to 80. Looking at the amplitude noise, it was below 130 all the way. Now it was 124 at 0.1 hertz. So, and of course I have returned to 11.3 dBm in power, since the higher power level was associated with much more noise. I checked one more time at 11.3 dBm, and results are very much the same. And I used to look at this one, 130.06 and 130.01. Okay, fine. Then I had tried at 1 decibel less, and it is half a dB better. I'm not so sure it's significant. If I look at other averages, they are very similar. And maybe it is a little better, but a very small difference. And then I have tried 9.3 dBm, and it's similar, no big difference. And then I increased power to 12.3, and as it turns out, it is not much different, but well, 128 as compared to 130. It is a significant difference. So I repeated that, 12.3, and this time 126, it's even worse. Now, what happened was what you can see here. I was doing measurement and suddenly spectrum widened. I can see here some structure, and I can see far out, half an hertz or so. There is much more. So first I was changing the attenuators a little bit up and down, because the difference, the big difference here, going to 12.3, is that I changed the attenuator settings here to 20 and 21, and here I went back, but I have inserted a 3 dB attenuator in each channel of the 2-channel receiver, far away from the input splitter, so variations in impedance due to another attenuator here is eliminated, and the results were very discouraging. And of course that's because of this event. So here I knocked on the box. Here I knocked on the box with my little hammer and restarted. And now what I see from 0.22 to 3.7 Hertz is 129.46. And that's not so bad. It is in the neighborhood of what I'm usually seeing, about 130. So there is an instability that occurs now and then, not often, but it happened here once. After I knocked with a hammer, I have these results, which are not so bad. I see at 2.2 up to 3.7 Hertz, I see 129.46. Not very far from the optimum values, around 130. So I have increased the power 1 more decibel up to 13.3 dBm, and then I see 128.09. The higher power, 13.3 dBm, gives significantly more noise. And I have taken the difference between the measurement number 9 and number 14, this one and this one, which was at 10.3 dBm. It shows a difference of about 3 decibels from about half an hertz up to about 3 hertz. But at very close separations, the measurement is more uncertain, so I don't know whether this is really significant. And at larger separations, the difference is also not so big. Then I have compared number 5 to number 9, and that gives a very striking difference. The measurement at 0.1 Hertz differs by 10 decibels and 0.15 differs by 2.8. Otherwise the differences are not so big. And at larger separations it goes the other way. Now the difference between number 5 and number 9, these two, you can see here, one is 11.3 dBm and the other is the other is 10.3 dBm, but the big difference is the frequency. Here it was 8.585. That means an offset from the 50 Hertz, offset by 8.585 Hertz. This is because the coupling capacitor has been maximum, which means I have to make the tuning capacitor much larger to get the gain down to get this power level. But here the coupling capacitor is smaller, so I have to reduce the tuning capacitor to get the desired power level. I will try to repeat this to see if there is something that has changed or whether this is a reproducible result. I have set the coupling capacitor to maximum gain and tuned the unit to get the same frequency and power level as I had in the measurement number 5. That is now labeled 15. And when I look at the difference between 5 and 15, I find there is no difference until I get to 0.3 Hertz. And then at 0.1 Hertz the difference is 9 decibels. So what I see here is the same as I had here. The very big difference at 0.1 Hertz still is there. So this was something special when I did that number 5, and I don't remember any special thing. I can run the SDR-IP in parallel with the system with the UADC4 and mixers. Here is the result from the UADC4. It started at the same time as this other, which is the SDR-IP. They have been running 12 hours now. And when I compare what I can read from the screen, this is what I see. A significant difference at 0.1 Hertz and also at 0.15, but then there is the same. And here there is some noise in the signal, so there is less accurate readings, but still it is the same result. So there is something special at very close range. I have increased the transform size by a factor of 2, and now at 0.1 Hertz the UADC4 gives me minus 85. And here is the SDR-IP, and at 0.1 Hertz it gives me, well, it's a little bit less statistically, but I would say here, that's minus 85. And when I look at other points close to the carrier, I see the same level with both systems, except at 0.05 Hertz, where the SDR-IP deviates in the same way as it did at 0.1 Hertz. The SDR-IP has done 452 transforms, but at the same time the UADC4 has done 646. So the reason for the deviation at very close spacings is that the transform is not big enough for the UADC4 with the extended size at 0.05 and with the original at 0.1. So I haven't found what was the special with this measurement number 5, but I found there is no difference between the UADC4 and the SDR-IPs. The average phase noise from 0.22 to 3.7 Hz is minus 130 and a little bit below that for most measurements at power levels up to 11 dBm. At 12 and 13, that is significantly degraded. So from this I conclude that the maximum oscillation level should be for an output of, let's say, 14 dBm. That's a criterion for how to design the buffer amplifier. This is the output configuration I have used for all these measurements. I found 10 turns and 100 ohms and a single pair of series connected pairs of diodes. I have doubled here and reduced that resistor. I see it as two 100 ohms resistors in parallel for each group of diodes here. So I should get a very similar performance. The problem is when I put 50 ohms here, which I do when connecting feedback, the amplitude becomes a little bit too low. And that's why I have done this. And I have checked and I don't see any significant loss in the amplitude noise when looking at this point. The input has been like this, 50 ohms and directly to the coupling capacitor. I have done an experiment tuning this capacitor to a larger value, so I have lost about 2 decibels of output power due to that. And I have measured the noise, the phase noise, with the UADC4 system as well as with the SDR-IPs and get very similar results. It is with a larger transform, so I cannot compare the average values directly. But when I plot the results, I get the square marks, like here, degraded at close separations. And then here they fall on the same points as the previous best measurement, the one I labeled 5. And then at even higher offsets they fall below. The measurement is perhaps a little bit noisy, so I could say they are the same. I think it's time to use the interferometer to see whether I can see this difference for mistuning the drains of that FET input stage. So in order to do that, I will feed directly on the FETs from a 50 ohm source, because the output impedance of the crystal on its resonance is close to 50 ohms. And then look to see what happens when I mistune with respect to the phase noise that I can look at with the interferometer. I run the interferometer like this. The Wenzel oscillator gives plus 13 dBm, the split in a hybrid. Then there is the phase adjust, and a 19 dB attenuator gives me minus 10 dBm. And that is what I need on the sources of the first amplifier to get plus 11 dBm at the output. Then I need 3 decibels of attenuation. Otherwise the signal is too strong to fit to this signal, which is adjusted in amplitude, just a small attenuation to make the level the same here. And then there is the hybrid into the analyzer. Here is the close-range phase noise with a carrier suppression of 40 dB. It is minus 78 at 0.1 Hz. Here is the amplitude noise. It is significantly lower, about 95 at 0.1 Hz. And the phase noise was 78. And the amplitude noise is at 0.3 Hz, below 101, while the phase noise was at 97. So the amplifier gives phase noise, which is a little bit surprising to me. I have reduced the attenuation here by 2 dB, means I have minus 8 dBm into the amplifier. And then I have increased attenuation here from 3 dB to 5 dB to have the same level here and to have the same nearly amplitude adjustment here to measure at the same signal level as before. Here is a 2 decibels higher signal level. The result is the same as before. The amplitude noise is very similar also, about 1 decibel better. The average phase noise over the region differs by 0.2 of a dB. That means it is the same, because the number of averages is not very large, 100 or 280. Similarly to before, I have increased this capacitor, this time for a reduction of the gain of 2 decibels. This time I see a big difference in the main spectrum. It just disappeared here, what I had before, but it was much narrower. And here is the phase noise, and here is the amplitude noise. The average phase noise has gone up from minus 86 to minus 80. That's 6 decibels on the average, and about 10 decibels at 0.3 Hz. The amplitude noise has increased much more, from 78 to 96, that's almost 20 decibels. 86 to 101, that's 15 dB. So it's more amplitude noise than phase noise. And here it's obvious that phase noise and amplitude noise have a common origin. The correlation, the yellow here is very far from zero. And the white is maybe a little different from zero also. The result isn't really so surprising. Here is the signal that is 40 decibels below the carrier. But when I turn that capacitor slightly, you see it behaves in an unstable fashion. Here I move it slightly. And I'm moving it gradually, and so there is a poor connection in the trimmer capacitor. The capacitor is this kind. Contact to the moving part is on the outer surface here. Some small fingers on the inside. I cannot see any way to bend them to increase contact pressure. But I can clean this inner part, and I can use one from another capacitor also to see whether I can find a more solid contact. Cleaning has not helped much. This is what I had before. This is without the center part of the capacitor. And here is cleaned. Another one which I have cleaned. It is a little bit better than here, but it's still very noisy. I have removed the center part of that capacitor, so it is now at its absolute minimum capacitance. And I have also set the carrier to 40 decibels suppression. And there is the result I see. Should be compared with this. What I saw here and here was at a much stronger signal because I didn't have the 40 dB suppression then. Here is the phase noise. The system has been running overnight, 8 hours and 45 minutes. The average noise is 87. So the noises I see here is just a little bit lower than before with the original tuning. I made a mistake and cleared the averages, but now I have been waiting 2 more hours, and here is the amplitude noise. And it's very similar to what I had before. So I should compare this column with that column, and they are more or less identical. And the amplitude and the phase noise, they are not correlated. I can see at 0.25 Hertz some small correlation, but when I zoom out to see up to 3 Hertz here, I can see that the correlation is not very strong, but it is almost constant from 0.3 Hertz to about 3 Hertz, while there is no correlation below 0.3 Hertz or so. The statistical significance of the phase noise, the amplitude and phase, is very good because the imaginary part is far below the signal, and the correlation signal is the same as the uncorrelated signal, which means that the phase noise really dominates, and that's because I have subtracted the carriers. I mean, it is an interferometer with 40 decibels of carrier suppression. And it is the same with the amplitude noise. The separation between the signal and the imaginary part is big, from 108 to 125, or that order of magnitude. And it gets a little bit less out here, but still signal to noise ratio of the amplitude noise signal is good. So what I found is there is one mechanism above about here, and another mechanism for the strong noise I see closer to the carrier. Here is the phase noise, 0.1 Hertz. It's minus 88, and 0.15 minus 92, and maybe a little bit better, but it's hard to say for the statistics. At very close range, the amplitude noise is well below the phase noise. But as frequency offset increases, they become correlated. At 1.5 Hertz, they are equally strong, and higher offsets, the amplitude noise is stronger than the phase noise, and the correlation is maximum at about 0.5 Hertz. So, I don't know what to say. They have the common origin, the noise around here. A lot of it has, not all. And when I take down the numbers, what I should compare with is this table, -8 input and 11 output, due to a mistuned capacitor. Previous time 76, now 88, 83.92. Phase noise has improved very much due to that capacitor. And the same, of course, with the amplitude noise. It has improved very much. But when I compare it with having no capacitor, there is a big improvement in the phase noise at close range, but in amplitude noise the difference is very small. Questionable whether there is any difference. I'm running the unit as an oscillator with that extra 10 pf on the drains of the first stage FETs. The result is not encouraging. I see here 83 at 0.1 Hz and 89 at 0.15 Hz. This is not particularly good. The average from 0.22 up to 3.7 Hz is minus 127.6. It should be below minus 130 when it's good. I have modified this transformer from 35 turns to 10 turns by filer. The wire is also significantly thicker, which means that the losses here are a little smaller, and the impedance at this point is lower, from 24 down to 21 ohms approximately. But it's also less inductive, which means that this capacitor is now a bit larger. As a result, the impedance here is reduced from something like 800 ohms to 680. I don't remember exactly, but it is a little bit lower anyway. When I start the measurement in the interferometer, this is what I see. A frequency change here, that's okay. But it's noisy, and here is a burst of noise, and an even stronger one, and then it calms down and looks much better. This was late at night, 3 o'clock in the morning, so I just reset collecting averages and waited to see what will happen. And now, 8.5 hours later, I see like this. Here the noise level is rather high, and we have these events. And here the noise is significantly lower for a while, and then there is an event again. And of course the result I see here is not particularly good, but it's not so bad either. Anyway, I have to find out what these irregularities are caused by. What I did was to replace this core by this one. When putting this significantly thicker wire in a twisted form onto this core, there is a lot of stress in the wire. Maybe it moves to release the stress gradually over a long time. I will attach it properly to the core with some glue to see whether it calms down. I haven't changed anything else, so I have to think that the problem is caused by the transformer. The only other change I made was to replace a capacitor for one with a slightly bigger value. I don't think that could cause the problem I see. I used some of this to glue the twisted copper wire to the core. It seems the situation is better, but there are still problems of the similar kind, as I can see here. But the very big events, they are no longer present. I have disconnected here, and I'm measuring the impedance at this point into the second amplifier. And it is 19.6 ohms in series with 223 nanohenries. With 220 nanohenries and the 36 ohm resistor to ground, I get the same impedance here when I connect my 50 ohm analyzer to this point, so I can see the performance of this first stage only, when loaded with the same impedance that the second amplifier normally loads it with. Here is the first amplifier stage in the interferometer with 40 dB carrier suppression. It's obvious I have a stability issue in this amplifier. Not so many components, so I should be able to find out which one or which ones. Now, about 7 hours later, I can see that this event was followed by a noisy period up to this point, and there was a stronger pulse, and then it is more quiet. And here is a new event. Here I have opened the box, and even when it's open, so I have a lot of infrasound noise, I can see irregularities, like here. Well, it could be infrasound, but it could be one of this kind of irregularities. At this point, I have entered the room and made some noise here. Anyway, with the box open, I can try to see if I can find some sensitive parts that are more likely to cause these kind of problems. I had pretty good results. I didn't make a video from that, but after that I have moved the connectors a little and ended up in this situation, which is a very big degradation. So I know I have a connector problem. Here I'm using the S-meter to look at amplitude as a function of time. And I look at the BNC connectors one at a time, like this. I turned it by 45 degrees or something. And this is the result. I can magnify it a little bit. And it's odd, it goes up to a peak and then it goes down. And here I turned it back. Well, I don't know what to say about that. That was the input, and here is the output. There was a stronger signal for a short time, and then it goes back. Here, this range, I moved a little on this N connector. I had it unscrewed and turned it a couple of degrees only, like this. And now I tighten it again. I have cleaned the coaxial connectors at the points marked by green here. These are things that I have moved frequently. Here I have to swap these wires if I need a 180-degree phase shift. And in this box there are 7 connectors, and here there are 8 plus 2 adapters. The things I have cleaned properly now are these BNC connectors, SMA connectors, adapters. In total 12 coaxial joints. This has made a significant difference. I only see 2 weak events, one here and one there. And I have recorded the phase noise. It is minus 86 at 0.1 Hertz offset and 92 at 0.15. Here is phase noise and amplitude noise up to 0.35 Hertz, and there is no obvious correlation here. It's almost 5 hours. The average is minus 91.2 dBc per Hertz in this range, and it's the best I have seen so far. and I'm still measuring with 40 decibels of carrier suppression. I have forgotten to say that while I was running the box open, I found that moving a little bit like this created significant amplitude changes. To fix that, I have improved soldering down here as well as down here. I could do that without disconnecting the trimmer. And that solved the problem. I don't see any sensitivity when moving here very carefully. The next step is to check the impedance at this point, so I know how to feed the second amplifier. When the crystal is not connected, I see 2.6 kilo ohms. With a 56 ohm resistor replacing the crystal, I see 398 ohms on a slightly lower frequency. The sweep width is 4 megahertz, so this is 2 megahertz below and 2 megahertz above. With the crystal in place, I see 522 ohms when the input is open. 520. It varies a little bit. If I look at here, the lower bound, marker 2, it says 2.6 kilo ohms and 1.3 inductive. And at the upper, it says 1.7 kilo ohms and 1.3, also inductive. With a 50 ohm dummy load on the input, the impedance on the resonance goes down from 520 to 512, or maybe 513. It also varies a little, of course. I feed the second amplifier through a 470 ohm resistor from a 50 ohm source to present it with 520 ohms in this point, as if it were fed from here. I had to insert a 6 dB amplifier here between the Wenzel oscillator and the first hybrid. And then I had to add 1 dB of attenuation at this point to get the desired output here as well as here at 13 dBm. There have been 2 events here in a 2-hour period. That has probably affected the noise a little bit, and the numbers I read are not very impressive. Minus 78 at 0.1 Hertz. The amplitude noise is much better. It's the white trace here, and here is the phase noise. I have operated these connectors, the input and output, when doing the impedance measurements on the amplifier, and also added this amplifier at the Wenzel oscillator output. To find out whether the glitches originate in the amplifier or if there is something with the interferometer, I have replaced the amplifier in the box with a straight through wire, and this wire will not give any glitches, so if they are still there, it's something in the connectors somewhere. I'm still running with 40 decibels of carrier suppression, but the signal levels in the interferometer are higher now, so I see more of the noise at the sides. The time now is 15 minutes past 4 in the afternoon. I have had glitches 2 times in a 2-hour period, so, well, around midnight, if there have been no such problems, I can feel sure the problems occur in the amplifier. And if I see problems, well, then it's outside. 5 hours have elapsed. There has been a single event of a noise pulse. The phase noise is very similar to before, which is odd. I take down the numbers as usual. And the amplitude noise is much lower. Phase noise and amplitude noise are not correlated, and the difference is very large here with much stronger phase noise. I don't think the phase noise originates from any of the components in the 2 legs of the interferometer. Maybe there is some correlated noise between the 2 oscillators I have. If there is a very small signal leaking from one to the other, there could be frequency pulling. I think frequency pulling would happen only at very close separations from the carrier. And that would fit with this. The white trace amplitude sideband noise is 1 over f. Each doubling gives 3 decibels. And that's valid all the way down to 0.1 hertz offset from the carrier. The phase noise I see is much steeper. I don't think phase noise can be generated by the components in the 2 legs of the interferometer. So most likely this is an error. Something happens between the oscillators that make them have correlated noise. Still, the level is very low, minus 118, minus 40, that is minus 158 dBc per hertz at 1 hertz. And minus 86 means minus 126 dBc per hertz at 0.1 hertz. That is a very low level, although it should be much lower, I think, because there isn't anything that could generate phase noise as far as I can understand.